Welcome guys. So in this video, I want to introduce a notation called commeasurable, which is really interesting. It's like a very old Greek idea to prove that the square root of 2 is irrational. Okay, so if this is the first time you see such an idea, that is really amazing. So be sure to subscribe to my channel if you want to see more interesting things. Okay, so let's quickly define notation. So the idea is that if x and and y are both positive number, then if there is this L which is positive, such that x is product of ML, y is product of NL, and n belongs to a positive integer, then we say that x and y are commeasurable. Okay, so one easy consequence is that x divided by y will be m divided by n, which is rational. So the idea is that if x and y are commeasurable, then their ratio are rational. Okay, so but actually the converse is true. Okay, so let me just. So converse means that if x divided by y are a rational number, then the x and y are commeasurable. And the reason is also easy, because if x and divided by y is rational, let's take a m to be m and n, which m and are integer. Right? So that means let's say I can divide it right. So let's say this ratio is I can that x divided by m just equals to y divided by n, and whatever it is, right? I just call it r bar, right? Because x is greater or equal to x is not positive, m is positive, y is positive, n is positive. So x can be written as m r bar, y is called n r bar, right? So they are commeasurable. So the idea is that if x and y are commeasurable, then only if their ratio are rational, right? If I define commeasurable to be this. Okay, so now let's introduce a small lemma. So lemma is that if x and y are commeasurable, so I mean I just want to show notation. X and y are commeasurable, and then let's say x minus y. Let's say if x greater than y, then x minus y and y is commeasurable. And the proof is trivial, right? Because x minus y divided by y will be just x divided by y minus 1, which is some integer minus 1, and also greater than 0. So just still a positive rational number. Okay, so this is a very easy lemma. Okay, so now we can prove the interesting things. Okay, so let's talk about a preposition. So preposition 1 is that right, if somebody give you a square, right? So one easy things that one easy fact that we have already learned at elementary school or something like junior high school or something. Then we know that that AC divided by AB is called the square root of 2, which is irrational. Right, but if you go back to the 2000 years ago, then people don't know how to write it. People don't have the square root notation. So that means people cannot use people do not have the irrational number idea, right? So people don't know that square root of 2 is irrational until someone proves that where the fact that we will prove it. So now let's prove that square root is irrational. So if you learn the junior high school, that people just write square root as p over q, and then you get p squared equals to q, 2q squared, and you say p equal prime, and then p is a number, p is divided by 2. So then you keep doing and you get contradiction, right? But now in this video, we are just using commeasurable idea. So let's suppose. So suppose not means that AB and AC are commeasurable. So I just use COM just for short. Okay, so remember this is square, right? So the idea is that if someone just smart enough and take D, right, just that. So I create let's say AD equals to AB. I just create this. So Then I have this. I just draw a line. I call it E. Okay. So the magic things happen. So magic idea is that if AB and AC are commeasurable, right? Then we create this. So it means that the AB and AD are commeasurable, right? Which implies that, so you see this is the same, right? And now you see this is these two triangle, right, are similar, right? Because exactly the same, because you already have the right triangle and the two sides are the same. So this guy will be the same as this guy, right? So from lemma, okay, so let's say from lemma we know that so now AB and so since AB and AD are commeasurable, right? But AC, so that means from lemma we know that AB and since AC and AD are the same line, right? So that means AB and CD are commeasurable because AC minus AD is just CD, right? So from these two. Then we also know that these two are the same, right? But not only that, this is 45 degree, right? And this is also 45 degree. So actually CD is the same as DE. So AB or DE are commeasurable, right? But now DE, now we prove that AB and DE are commeasurable, right? But now AB is the same as BC, right? So BC and DE are commeasurable. But the idea is what? But the idea is that the DE and BE are the same, right? But BC minus B, so this BC just can be written as BE plus EC, right? But since DE is the same as BE, so finally we got EC and DE are commeasurable. So that means DE and EC are commeasurable, right? But you see there's a contradiction, right? Because we get a smaller triangle, which we say is that the one side is the right triangle, and we say that this guy and this guy are commeasurable by L. So originally we say that AB and AC are commeasurable. That means is this L, such that AB are L times some integer, and AC are L times some integer, right? And from here that we get this small right triangle has the same property. So the DE and the CE, so DE and CE are commeasurable, right? But that means what? That means we can do the same thing, right? We can think this small right triangle is the same large triangle, large right triangle here, right? So that means we can do the same technique and create a more small one. So we can keep doing, right? But this right triangle can be arbitrarily small. So until some step, one side of that right triangle will be less than L. Its length will be less than L, right? So it's contradiction. Right. The idea is that if we start from a right triangle and we suppose that one side and its diagonal one side is diagonal is commeasurable, then we can create a smaller triangle, this small right triangle, and say that this DE and CE are still commeasurable. And then you keep going, that you will get a small right triangle. Then until one right triangle, one side of that right triangle is less than L. But then this contradiction, because for that triangle, which is that side is smaller than L, which cannot be commeasurable, right? Because the reason is easy, right? Suppose AB is commeasurable by L, then AB must be greater or equal to L, right? Otherwise, there's no integer can put in here. Okay, so let's prove. So this proves that the AC divided by AB is not rational. It's not a rational number. So it proves that the square root of 2 is irrational. Okay. Okay, so this is the first example that why people this is the old Greek idea that why people talk about how to prove the square root 2 is irrational, just use the commeasurable idea. Okay, in the next video, I will prove actually this is the historical fact that also very famous that the AC divided by AD for the regular pentagon is irrational. So this is very famous proof, and the people that guy found this proof I think it's put to death, right? and throw into the sea because he found something which is maybe offended to God. Okay, so this is the old Greek history, right? But the things that the next video we will prove this regular pentagon, which ACR and AB is not commeasurable or incommeasurable. Okay, that's it then. I will see you guys in the next videos. Be sure to subscribe to my channel. Thanks.